Hello, and welcome to a lecture on the concepts of nuclear physics. We're not going to really work out problems here, just going to talk about the conceptual side of nuclear physics. This is the first of two lectures. In the second lecture, I'll go over the details of radioactivity and the types of data that can lead to. In this first lecture, I'm going to talk about the phenomenon and the physical explanation that leads up to radioactivity. Why should we expect certain atoms to be unstable and decay into other atoms? Okay. So since we are talking about the nucleus of an atom, and we've zoomed in from our previous discussion about the atom as a whole, including electrons, since we're talking just about the nucleus, we need to get some details out of the way to understand what are the values that we care about inside the nucleus. Physicists and chemists take a pretty similar view to nuclear values, except for, of course, some of the ideas of the wave nature of matter and so on. But let's get some of these basics out of the way. These following reading questions are just to show the types of ideas that are going to be presented in this lecture, some in this first video, some in the second video. So let's take a look at one of those questions. You should try to answer this. If you can't, that's fine. Just it'll give you an idea of the stuff that you'll need to learn throughout this lecture and the reading. So an isotope has a mass number of 13, and it's got an atomic number of 6. So we have two different kinds of numbers. How many neutrons does this isotope have? Well, A is the letter we give to the mass number, okay? And that's, in this case, it's 13. The atomic number is represented by 6, okay? Now, the atomic number is interesting because the atomic number determines how many electrons a neutral atom would have, okay? And it determines how many protons there are in the nucleus. So the atomic number is always the number of protons. And that number, the atomic number, sets the element. So every element on the elemental table of element, okay, is set by its Z value, by its atomic number, not by its mass number. And that's interesting because why should the atomic number, why should protons be so important? Well, because protons for neutral atoms match the number of electrons. It's electrons that really tell us about the behavior of the atom with other atoms in terms of its bonding ability. So that's what we care about, and that's why the periodic table reflects that number. But of course, the mass number is also important, and sometimes it matters. It matters for things like mass spectrometry, if we're looking at the actual kinematics, because different size atoms will behave differently because they have different amounts of inertia. And that refers to the total number of nucleons. And nucleons are protons and neutrons. And we'll be talking about this more in just a second. Okay, so if that's the case, if nucleons is the total number and it's protons and neutrons, and there's no other type of nucleon, it's either a proton or a neutron, then we should be able to find the number of neutrons, can't we? If we just subtract. So indeed, there's 7 neutrons, one more neutron than proton. Okay, the number of protons and neutrons are certainly not always equal. When they're not equal like this, when there's more neutrons or fewer neutrons than the number of protons, that's usually called an isotope. Truly speaking, every element is an isotope. An isotope just refers to any combination of protons and neutrons. However, the most common isotope is just usually referred to as the base element. And then the more exotic versions of that element, when there's extra neutrons, for example, is called an isotope of such and such element. Okay? So now let's talk a bit about the energy inside the nucleus. So let's read this one. The bound system of any given isotope has a lower mass than of its separate component protons, neutrons, and electrons. How can this be explained? So a system together, and this very small piece of matter just composed of the nucleus and the electron orbiting it, most of the matter, of course, being contained in the nucleus itself, how can that weigh more? How can the sum of all those individual parts be greater than the weight of the parts if you split it apart? All right, so take a look at the options. What do you think is the best answer here? Thinking about what we know about atoms, about the nuclei of atoms. Okay, so it's fine if you don't know this one yet, but it's the idea that the difference in mass is because the energy equal to the binding energy of the nucleus has left the system. So some of that mass, right? Some of that mass of the isotope was transferred into pure energy by E equals mc squared. Some of it stopped being mass and became energy because what was functioning as mass was actually just the binding energy between other mass. But that's true of any mass. Mass is just a type of potential energy, a type of binding energy. And we see it here between these fundamental particles of the atom. Okay? So onto another isotope. All right, 99 Tc, which has a half-life of 6 hours, is used in medical diagnoses, procedures, such as bone scans. If a sample has an activity of 32 millicuries, when initially prepared, what is its activity 9 hours later? So this is the type of idea activity rates and the exponential decay of those activity rates that I discussed conceptually in the second of these two conceptual videos, and also is the one computational subject from this chapter. Really the one type of problem that we can work out computationally in terms of percentages of samples remaining that have a particular half-life or calculating a half-life due to behavior. These are the type of ideas, okay? So what's going on here? Well, there's less than 16 millicuries, but more than 8, okay? Because we have completed more than one half-life. So we've cut the population in a half, we've cut the rate of decay in a half, and then some. So that gives us an idea of where the current activity rate of decay must lie. Because that's what half-lives and activity rates, decay rates are all about, is this idea that we cut it in half subsequently every half-life period of time. So if you have a total amount, you cut it in half after a half-life, then that half, you cut that half in half after another half-life has passed, and so on. You just keep cutting it in half, getting a smaller and smaller piece. And you cut that smaller piece in half each time, okay? So here is a decay, a particular radioactive decay producing a positron and a neutrino and a product of the decay, actually changing elements, okay? This is the idea of radioactive decay. It changes the element. One element becomes another. So what type of decay is this? If we're producing a positron, what type of radioactive decay is that? Well, that is referred to as beta decay, specifically beta plus decay. All right. There's also beta minus decay where an electron is produced instead of a positron, also completely possible. But positron decay, beta plus decay is the more common of the two types of beta decay. But what they both have in common is that either a positron or electron is produced, which are the same particles, just opposite charge, okay? Two similarly charged particles are approximately 5 femtometers, that's 5 times 10 to the negative 15 meters, okay? What happens when they're that close? Do they move together due to the very strong nuclear force? Do we not have enough information? Are they balanced, or do they repel each other? Well, it turns out they repel each other, because in order for like charges to actually be held together by the strong nuclear force, which does hold together protons, which after all are light charges, so you could have, say, 3 protons in a helium-3 nucleus, all held together with a couple of neutrons, the force that holds those like charges together only operates at distances that are going to be less than those 5 femtometers. So this is a great enough distance that the Coulomb force would be stronger than the nuclear force, and it would pull them apart. Okay, so now let's get into this introduction leading up to radioactivity. Okay, so first the basics about the nuclei, the terminology I was referring to a moment ago. The atomic number, represented by Z, is the number of protons. Good. The neutron number, represented by N, is the number of neutrons. And the mass number, A, is the number of total nucleons. Okay, so for example, we have an element X, just a mysterious element. Z is always represented over here on the left in a subscript, and then A is represented on the left as a superscript. All right, so mass number is the upper number, and then atomic number is the lower number. And so here is an example with aluminum. And you look here, and you see right away the mass number is represented. Okay, this tells you this mass number can also and often is a decimal, so maybe something like 27.113 or something. Why is it the only one that is ever represented as a decimal? It depends on the version of the periodic table you're looking at. But the reason sometimes the mass number is represented as a decimal is because it represents the average of all the isotopes, taking into account how often they're found in nature, or at least on Earth. Okay, so it talks about like kind of the population, the total population of isotopes and how many exist with particular mass numbers, and then it takes a weighted average, and that's the value you actually see reported. Okay? All right, and that's because certain elements tend to exist with a certain number of extra neutrons, and that's especially what we see of heavier elements. There's always going to be more neutrons than protons, and we'll talk about why that is in terms of the stability, but That's just a common phenomenon. But when we do look at this, the one number that isn't shown, of course, is the neutron number. And that's because we have to calculate it. And the simple calculation is just to say that n in this case would be 27 minus 13, because everything that's not a proton is a neutron. And so in this case, it would just be 14. Okay? All right. So here are some different isotopes of carbon. Okay? All right? And some isotopes of hydrogen. Now, hydrogen isotopes are so important because it's such an important fundamental element, fundamental atom, that hydrogen with one proton, no neutrons, and thus a mass number equal to its atomic number is the most common. That's basic hydrogen. All right? Now, deuterium is considered an isotope. Again, not because that's the strict definition of an isotope. An isotope can just be any combination of neutrons and protons, but because it's less common than hydrogen, well, we call it an isotope of hydrogen. And it has still one proton because it has to in order to be hydrogen. You can't have any different number of protons. You have two protons, you're helium, no matter how many neutrons you have. But since we see that the mass number is now 2, that tells us that our number of neutrons is 1. Now we actually have a neutron. So it's kind of interesting that basic, most common hydrogen doesn't have a neutron. It's just a single proton, where deuterium, a less common version of hydrogen, actually has a balance of one neutron and one proton. You can also have tritium, which is much rarer still, where you have 2 neutrons, thus the mass number is 3. Okay, so looking at the masses of the proton, the neutron, and the electron in some various units, in kilograms, of course the base unit, in atomic mass units, and in the units that are particularly well suited to relativity, which is expressing them as mega electron volts per the speed of light squared, we can see that there's some variation. In particular, we see that neutrons are slightly heavier, all right? The neutron is slightly bigger than the proton, okay? Well, why is that? Well, because the neutron is essentially a proton plus an electron. And I'll talk about that more in the second video when we talk about beta decay, because beta decay, where electrons are produced from inside the nucleus, begs the question, where do those electrons come from? If they're coming from inside the nucleus, typically electrons are, of course, in the electron cloud outside the nucleus. Well, electrons can come from the nucleus because a neutron plus an electron, well, can give you, or rather let me rewrite that, a proton plus an electron can give you a neutron. So you can actually either have a proton lose an electron, gain an electron and become a neutron, or more likely, you can have a neutron lose an electron and become a proton, all right? And in that process, the neutron becomes slightly lighter, okay? It becomes slightly lighter. It actually gave up that electron. The state of the neutron can become the proton, all right? And we see that with the weights, because if we take the weight of the electron and we add it to the weight of the proton, we get approximately the weight of the neutron. Is it an exact match? Well, no, because there's some binding energy that actually holds that together. By the way, that wouldn't be the strong nuclear force. That actually has to do with the weak nuclear force that prevents neutrons from becoming protons. All right, so the most common unit we use with atomic physics is the atomic mass unit, 1.66 times 10 to the negative 27 kilograms. All right, and then we can see that the rest energy of one atomic mass unit of mass is 931.5, we round to 4 significant figures, mega electron volts. So that's how much energy there is in one atomic mass unit, okay? And one atomic mass unit is about the weight of a proton. Of course, it depends what atom that proton is in, but as we saw, it is pretty close to being a proton, all right? And in this mass here is proton on its own. Because I just a moment ago I said it depends what atom that proton is in. Why does that matter? Well, because protons effectively weigh less in certain atoms. Why? Because of that binding energy I was talking about a moment ago. Okay, but we'll talk about that with stability. Okay? And here then is the atomic mass unit expressed in those relativistic units, or just units well suited to relativity, which is mega electron volts per the speed of light squared. Okay? All right. So the size of the nuclei. How does the nuclei hold together, and why do those protons not just push apart from each other? Okay, so if we bring some like charges together, they will repel each other. Okay, unless we can have the distance be so close. So an alpha particle approaches a nucleus no closer than the distance d because of the repulsive electric force between them. That's the Coulomb force. All right. So here we see the repulsive force between them. All right. We have a balance of forces, or in this case, a balance of energies. We're saying the kinetic energy of the incoming alpha particle, an alpha particle just being 2 protons, as well as 2 neutrons, but here we only care about the charge. All right. So this is the mass of the alpha particle. So whatever amount of kinetic energy it has, that kinetic energy will become electrical potential energy. All right. So that's what this is right here, just electrical potential energy. All right. And that electrical potential energy is going to be based off of how many protons there are in the nucleus that we're trying to crash the alpha particle into, and then it's going to get repelled. Okay? And so that's the distance. That's the distance of minimum approach, okay, depending on a certain velocity and mass that we're trying to smash together. Okay? And that ends up being about 1 femtometer. Okay? In many cases, it's going to be in the range of 1 femtometer. Right? That's how close we can get before electrostatic repulsion is going to push the particle back. Okay? So then we see, well, if we do get that close, and 1 being less than 5, tying in with the reading question, then we see that we actually can get up to the point where we can have them overcome the Coulomb force and be held together by the strong nuclear force. So we end up with a radius that is justified by the strong nuclear force being greater than the Coulomb force. So the strong nuclear force greater than Coulomb force. All right, because otherwise it gets repelled, otherwise it gets pushed back. Right, but if we get in that range of about 1.2 femtometers, so 1.2 femtometers, then the strong nuclear force wins out and the nucleus will hold together. Okay? So that means that we have a stability, a point of how atoms can hold together. And it varies with the size of the atom, the size of the nucleus, the number of protons that are inside. So let's take a look at that with this graph here. On the vertical axis, we have the neutron number, and on the horizontal axis, we have the proton number. And we see that as we get bigger and bigger proton numbers, which means heavier and heavier elements, right? Starting with the very light elements like the hydrogens and heliums and carbons and oxygens, and moving up into the metals, heavier elements, all the way up into things like gold on the heavy end, right? As we move to those heavy elements, notice what happens with the relationship between the number of neutrons and the number of protons. Well, we start to get more neutrons, because if we kept an equal number, we would follow this dashed line here. But we don't. With the heavier elements, we are significantly above the dashed line. That's because we have more neutrons per proton. So more neutrons per proton for heavy elements. All right, and although we're not getting into the details, the numerical explanation why, it has to do with that binding force and with there being enough mass, enough inertia to hold things together based on their energy, and the number of neutrons is necessary to hold those atoms together and not have the Coulomb force tear them apart. Okay, so we indeed see that this stability continues up. All right, so let's take a look at the difference between the shaded region and the black dots. So the stable nuclei lie in a narrow band called the line of stability. The shaded areas show the radioactive unstable nuclei. Okay, so we have stable ones that are not radioactive. That's any of the black dots. All right, so these would just remain that element. But there are plenty of other isotopes that exist, which aren't shown as dots, but instead just a gray region. But they would continue to be particular combinations of an N value and an A value. All right, and making a total, or rather a Z value, making a total value of the element or the isotope. But the point being is that those are all unstable. All the ones that aren't the black dots, all the combinations, all the isotopes that exist that would be represented on this graph, they're all unstable. Either they're decaying in terms of producing alpha particles, all right, which is one type of nuclear decay, or they're decaying by producing beta particles, either positrons or electrons. Alpha particles are combinations of 2 protons and 2 neutrons. There's really no other particles that are produced from the nuclei. what we'll talk about a third type of radioactive decay called gamma decay. That's always follows a beta decay or an alpha decay, and it's because when a neutron decays, sometimes it'll, or a nucleus decays, excuse me, it will decay into an excited state, and it's as its new element, and that it's just like the excited state of an electron, but it's an excited nuclear state. And then as that nuclear state relaxes, as that waveform, that matter wave relaxes to a less excited state, it releases a gamma ray, which is a very high energy photon. But the point being is that there's all these unstable combinations, a lot more than the stable combinations. Although we can see there's quite a few stable combinations for that matter. A lot of these black dots, right, and very interesting combinations. All right, and these were discovered experimentally. There are some theories that explain why we have weird clusters, as you see. But certainly there are some general rules like more neutrons per proton. All right. Now, what about that binding energy? What about that idea that we can talk about the effective mass, or the mass becoming energy, or vice versa, but particularly in this case, mass becoming energy inside of a nucleus. Why does it vary per element? Well, because we have this very interesting phenomenon going on. The total energy of the nucleus is less than the combined energy of the separate nucleons. The difference is the binding energy. Okay? That binding energy explains the difference. So there's energy contained in holding the nucleus together. And what's going on? What's the comparative binding energy between elements? Well, let's take a look at this graph, because this graph has a wonderful story to tell. On the vertical axis, we have binding energy per nucleon, measured in mega electron volts. Okay? All right, excellent. Going up, increasing in value. On the horizontal axis, we just have mass number. All right, just our mass number of our element, just being the number of protons plus the number of neutrons. So we start off with our H2, all right? So here, this is deuterium showing right here, all right, as opposed to just hydrogen. But we see that there's a particular amount of binding energy. And it wouldn't make sense to show the binding energy for just a proton, because there's nothing else in the nucleus. So there really is no binding energy for just a single proton, but there is for deuterium. And we see that there's not a lot of binding energy for deuterium. There's a relatively small amount of energy holding that one proton and one neutron together. But then when we go up to the next element, helium, we see that there actually is quite a bit of binding energy. The binding energy has shot up dramatically from about 1 mega electron volt to about 7 mega electron volts. That's a huge difference. So what does that mean? Well, that means that if we fuse two hydrogens together, then we're going to get something that produces energy. All right? So if we take hydrogen, deuterium, H2, and we put them together and get ourselves helium, just basic helium, we're also going to produce a lot of energy. And that's because there's a lot more energy, binding energy at least, in the helium atom than there was in the hydrogen atom. And that huge increase in the binding energy of the helium means that we had some of the mass go away. Some of that mass became pure energy. And it turns out this excess energy, some of it just becomes light, so it can just become gamma rays. That happens in the fusion that occurs inside of our own star, our own local star, the sun. But also that energy, becomes kinetic energy of the particles involved in the reaction, in this hydrogen plus hydrogen, deuterium plus deuterium. Okay, so that means that would be an energetically favorable process to fuse together two deuterium like this, because the binding energy goes up so much. And we can see that continues to be the case. If we put together smaller elements, then we continue to get more energy, right? Not so much, definitely not going from hydrogen to lithium, but then as we go from lithium to barium and boron and nitrogen and iron, right? And then we can continue on to calcium and so on, or at the chlorine. We continue, the jumps aren't nearly as big. So the hydrogen to helium is a rather special jump. It's a huge one, but we still get more energy, all right? I guess we did drop when we went from carbon to nitrogen. That was actually, we would have lost a little bit of energy there if we just took two carbon 12s and tried to put them together to make a nitrogen. But obviously we wouldn't get a nitrogen. If we put together two carbon 12s, we get something with 24. So we'd actually be over in this range. So it would be energetically favorable. But point being is that there are these little gaps, but still, the trend is up, okay? We're getting more and more binding energy per nucleon, okay? So greater and greater binding energy up to a point, because we get right up here, this region of greatest binding energy per nucleon is kind of in the shaded region. Often we say that it falls right at, so this was actually fluorine over here, but iron represented right here, we say that the binding energy peaks out right at iron, or right around nickel. But somewhere in this range between iron and nickel, depending on the isotope, we have maximum binding energy per nucleon. And maximum binding energy per nucleon means less mass, effectively, less effective mass per nucleon. Because that means, because you can't have it both ways. If you got more binding energy, then you effectively lost mass. So that means that we can continue to fuse particles together up until we get to this maximum point, right around iron and nickel. Because then what starts to happen is, as we move into the heavier elements, we actually start to get less binding energy per nucleon. This is where fission, breaking things apart, produce energy. Because if we break apart, say, uranium, then we're going to get two elements that have greater binding energy. That means that they have less mass per nucleon, and that means that that mass had to become energy. That means breaking uranium apart produced energy. Whereas just like I was just saying, breaking apart all these heavier elements, like lithium, for example, would have lost us energy. So that's the trend. It actually goes up at first for light elements, more binding energy per nucleon, peaking out right here with this band of greatest binding energy per nucleon, and then gradually falling all the way up to these fundamentally unstable nuclei like uranium, but then really reflecting this idea that there's a trend. All right, and so that means that on this side, fusion produces energy, on that side of the peak, and on this side, fission produces energy. Okay, it all has to do with E equals mc squared and the binding energy per nucleon being a function of the mass number. Okay, so that's really has to do with nuclear processes, but it's a wonderful view into what the nucleus is all about. Because what we're going to be talking about with radioactive decay is really these particular phenomenon of releasing alpha particles and beta particles and gamma rays from excited states, which is really associated with these heavier elements, because they're going to be the ones that are more likely to be unstable. But it's still all part of the nucleus, so it's so important to understand a concept like the binding energy. And I'll leave off there, because in our next lecture, we'll be talking about radioactivity and the particular processes of one element transmuting into another. Well, thank you so much for watching this introduction to the nucleus of an atom. I hope it has been both interesting and informative.